On clear summer nights, we have long watched in awe as a broad band of light rose up across the sky. Now we know that behind this luminous veil of gas and stars, a restless universe is being shaped by shattering collisions, explosions, and shock waves. Two groups of astronomers are tracking a star that has accelerated to mind-boggling speeds. They believe it holds clues to the origin and nature of a mysterious object that's lurking deep within the galaxy. What are they learning about the supermassive black hole at the center of the Milky Way? To observers in distant space, our Milky Way galaxy would look something like this. A flat spiral with vast arcs of gas, dust, and about 200 billion stars swirling around it. The center, bulging up and out of the galactic disk, is tightly packed with stars. Thick dust and blinding starlight have long obscured our view of the mysterious inner regions of the bulge. And yet, the clues had been piling up that something important, something strange, is lurking there. The first to take notice was the physicist Carl Jansky back in the 1930s. He had been asked by his employer, Bell Telephone Labs, to investigate sources of static that might interfere with what it saw as the killer app of its time: radio voice transmissions. Using this ungainly radio receiver, Jansky methodically scanned the airwaves. He traced most of the static to thunderstorms, nearby and far away. There was one signal he could not explain. It was a hiss of radio noise that sounded like steam. Jansky narrowed it to a region in the sky, the constellation of Sagittarius, in the direction of the center of the galaxy. Located within a larger pattern of radio emissions, Jansky's source would become known as Sagittarius A. Word of Jansky's finding got out. He assured the public that it was not aliens seeking contact. Whether it was or wasn't, no one could really say for the next 3 decades. Then a young astronomer named Eric Becklin got interested in probing deeper into the galactic center.
Sagittarius rises right about there. First comes Scorpio around midnight, and then Sagittarius and the very big Milky Way and the very core of the galaxy.
Becklin is one of those rare researchers whose curiosity and determination push our understanding to a whole new level. It was the 1960s, and astronomy, like society, was in a period of ferment. Astronomers were peering into ever more distant corners of the universe, looking for answers to a whole new set of questions. When Eric began his career, a class of extremely powerful radio beacons called quasars had just been discovered in distant space. What powerful objects were generating them? did they come from the bright centers of galaxies, as some astronomers suspected? To look into the center of another galaxy, you have to pinpoint its precise location. Young Berkeley first took aim at our luminous neighbor, Andromeda. In this recent ultraviolet image, you can see a dense glow in the middle. Berkeley found the point where the light reaches peak intensity and marked it as the center. From our orientation in space, the Andromeda galaxy is in full view. But our galaxy is a different story. We live inside it. To pinpoint its center, Berkeley had to find a way to see through all the dust and gas that obscure our line of sight. He went to a military contractor and obtained a device that reads infrared light. Its wavelengths are similar to the distances between particles in a dust cloud, which allow it to move right through the dust. Looking toward the galactic center, Berkeley began measuring the brightness of infrared light as it rose to a peak, marking its exact location. Thus began Berkeley's long quest to see what lies deep in the Milky Way's heart.
Well, that this is the center of the cluster.
Berkeley wasn't the only astronomer interested in the galactic center.
Sagittarius star can be a black hole. Now we know, of course.
Reinhard Genzel
But nevertheless,
and
this
a
is bit
team
of a puzzle
based
that
at the
there's only
Max
a
Planck
blue star
Institute for Extraterrestrial Physics in Germany
We have a
began a
fighting
similar
chance.
campaign in 1990.
More than a fighting chance.
They came to the mountains of Chile and South America to use the recently christened New Technology Telescope of the European Southern Observatory. A few years later, in 1993, high atop Hawaii's Mauna Kea volcano, Eric Berkeley and colleagues, including Andrea Ghez, began using the giant new 10-meter Keck telescope. The American and German groups shared the same goal, to identify the source of radiation first observed by Carl Jansky. They found that most of the energy is coming from a region they called Sagittarius A star.
This is our roadmap. And that's the center of our galaxy.
That is too small and dim to actually see. That was not true of stars that are orbiting around it. Tracking the precise locations of these stars would take the sensitivity of Keck's wide aperture.
You can ask, how well can we position stars in our field of view? And it's, we can position things to 2 centimeters in LA as viewed from New York. So you can basically tell somebody's waving like this with their finger in Los Angeles as viewed from New York.
It's powerful enough to detect an object with the luminosity of a candle on the moon. Meanwhile, astronomers had focused the new Hubble Space Telescope on a different galaxy. A giant elliptical cloud made up of nearly 1 trillion stars 50 million light-years away, called M87. They tracked gas whipping around its center at speeds of almost 2 million kilometers per hour. That led them to calculate the mass of the gravitational source at M87's center at 4 billion times that of our Sun. This measurement, the first of its kind, pointed to the presence of a black hole of truly supermassive proportions. But that did not conclusively prove its identity. If a supermassive black hole lay at the center of our galaxy, the German and American teams each hoped that Earth's proximity would allow them to assemble conclusive evidence. Their search was part of a larger effort to map the layout of our galaxy and find clues to its history. Astronomers were eager to train a new generation of space telescopes, the great observatories, on the galactic center. Using Hubble, astronomers documented vast arcs of gas heated up by ferocious winds from large stars. Capturing infrared light, the Spitzer Space Telescope picked up the swirling heat signatures of dense star concentrations. The Chandra X-ray Observatory recorded multiple sources of high-energy radiation, most likely given off by ultra-dense neutron stars and small black holes. Based on Chandra data, scientists estimated that a swarm of 20,000 black holes likely inhabits the inner 3 light years of the galactic center.
If you would stand in the center of the galactic center right now, first of all, there would be stars all around us. You know, very unlike the situation we're used to, where we have one sun in that direction, that's it. There will be stars all around us. And very massive stars, lots of radiation. It would be we couldn't exist there. There's lots of ultraviolet radiation. X-rays are floating around, gas clouds bash into each other. And then, of course, the black hole itself, from time to time, accretes material and then releases radiation. So it's a very hostile environment, really.
To show there's a supermassive black hole in the center, the teams would have to prove that it's confined to a very small region and that it has enough gravity to whip the stars orbiting it to high speeds. The light of these stars travels 26,000 light years to reach us, only to be blurred in the last few kilometers as it hits the Earth's atmosphere. So both teams turned to new methods designed to sharpen the light.
16 is right there. Here, yeah.
The idea was to snap thousands of pictures in a short time. Because the atmosphere is in motion, a star's apparent position may shift from image to image. To pinpoint the star's true location, a computer averages the positions and looks for correlations in the wavelength of the star's light. The first few years' data allowed the teams to calculate the speeds of these stars and their rough trajectories around the center.
These stars are going as fast as 10,000 kilometers per second when they go through closest approach. That's going about 3% the speed of light. Keep our fingers crossed.
That allowed them to narrow the position of their target and to calculate the strength of its gravitational pull. That gave them its mass, roughly 3 million times that of our Sun. Because no other single object is known to weigh that much, it was strong evidence of a black hole. But it was still not ironclad proof. Their data, for example, didn't rule out a dense concentration of stars packed into the center, held there by their mutual gravity. The proof the team sought would come in the wake of an extraordinary event. In the early years of the new century, large telescopes around the world began to install upgrades. Most large new telescope mirrors these days are thin, designed to be mounted on metal scaffolding. Behind the mirrors, engineers install pistons and motors to subtly correct the shape of the glass as changing temperatures deform it, or as atmospheric turbulence blurs the incoming light. To these adaptive optics systems, they added lasers, designed to project an artificial star onto the upper atmosphere. As turbulence distorts its light, a computer subtracts the same degree of distortion from the light of the real stars, bringing them back into focus. This is a Keck telescope image of the galactic center. Without adaptive optics applied, and with it. This increase in sharpness allowed the teams to see what happened in 2002. The German team had begun making observations from the new Very Large Telescope Array at the Paranal Observatory in northern Chile. In the spring of that year, one of the stars they had been following, known as S2, made a dramatic move. S2 suddenly swooped around the center, accelerating to an astonishing 18 million kilometers per hour. The American team saw it too. It had come incredibly close to the suspected black hole, about 3 times the distance between the Sun and Pluto. If there had been a cluster of stars in there, S2's path and its light would have wobbled. It did not. This was the evidence the teams had sought. It showed that Sagittarius A star is a single object. Without doubt, it could now be called a black hole. This observation came at a time when astronomers had begun to believe that supermassive black holes play an active role in the evolution of galaxies. They had found that they occupy the centers of nearly every large galaxy. In fact, the larger the galaxy, the larger the black hole. That suggests that the two must have evolved hand in hand, each shaping the life story of the other. As matter flows into a black hole, it heats up to millions of degrees. Despite the black hole's intense gravity, much of the inflowing matter blows off in fierce winds and shoots out in powerful jets that roar out of its poles. The more matter that rushes in, the more the black hole pushes back out. The force and heat from an active black hole can have the effect of limiting a galaxy's growth by slowing star birth and by pushing gas out of its central region. As a result, a strict relationship has developed between the size of the black hole and the size of the galactic bulge that surrounds it. The astronomers wanted to know, is the Milky Way's own supermassive black hole still active and growing? Or has it gone dormant? Just as the black hole that Sagittarius A star revealed its existence, it would show its true colors. The year 2001. Scientists were beginning to work with the recently launched Chandra X-ray Space Telescope. They pointed it at Sagittarius A star, and by chance, at that moment, the black hole erupted. The teams on the ground began focusing on it for longer periods, hoping to see it happen again. And so they did. They saw what are now thought to be flares, outbursts that take place when matter builds up near the event horizon. When it falls in, around once an Earth day, the black hole lights up.
Okay, here we can clearly see a region between those two sources where there is no other object. And here we have the same region, the same two sources, and now in between we see an additional source. So this is a flaring state of Sagittarius A star.
As gas clouds, if you like, come in, they sort of spiral into this innermost regions and get ever hotter before they disappear. And in the very innermost region, just before it disappears from our sight, that's where they would be the hottest. And so an accretion event, think of it sort of a clump, falls into the center, could also look like that.
A group of astronomers is now making plans to get a closer look at these flares, and perhaps to directly glimpse the black hole. From Earth, it is but the size of a grapefruit on the moon. No single telescope on Earth has enough resolution to see something so small, so far away. Astronomers think that they will be able to see it by linking observatories around the world to create what amounts to an Earth-sized radio telescope, known as the Event Horizon Telescope. This simulation shows what they expect to see. A supermassive black hole in silhouette, framed by eruptions on its surface that travel around the monster as it spins.
The reason that this periodicity, the fact that things change repetitively in the same way over a certain time scale, is that the material's orbiting the black hole. And so this time scale corresponds to the time it takes to go completely around the black hole. And so that also tells you how close it is to the black hole. And the key here is that if the black hole's not rotating, if there's no rotating, the shortest period that you should be able to detect is about 24 minutes. So if it is rotating and you think it is coming from the accretion disk, then that's telling you that the black hole's spinning, because material can get closer if it's spinning faster.
Meanwhile, astronomers have mounted a major effort to map the turbulent environment of Sagittarius A star, to shed light on the monster's current state and how it might change. The great space observatories, Hubble, Spitzer, and Chandra, combined to produce the most detailed image yet of the galactic center. In this image, the central zone, 160 light-years across, stretches out like a vast claw. Sagittarius A star is the X-ray hot region on the lower wrist. Out on the hand is a dense grouping of about 1,000 stars, called the Arches cluster. It formed just a few million years ago. Only its tight formation saves it from being torn apart by the intense tidal forces of the center. Below is the Quintuplet cluster, with the largest star documented in the Milky Way. The Pistol star weighs in at 150 times the mass of the Sun. Large stars like these generate fierce winds of plasma that fill the galactic center. They should provide a steady diet for the black hole and cause it to glow brightly. Monitoring X-ray emissions with the Chandra telescope, astronomers found that these and other large stars are just a little too far away to feed the monster. As gas swirls in, a portion heats up and pushes outward. This outward wind is enough to block much of what's flowing in. So what would cause it to flare up? A separate study suggested that what's falling in is not gas, but comets and asteroids that had been stripped away from stars whose orbits had brought them in close.
This is the center of the cluster, and you know, Sergei's star was over there.
The black hole remains in a state of semi-retirement.
But nevertheless, this is a bit of a puzzle that there are so many of the blue stars.
Will it become active again? Working in the cold, clear air of the Antarctic, one group of radio astronomers surveyed the broader region surrounding the galactic center. Data from their South Pole telescope contain signs that a spectacular flare-up is slowly materializing. A huge ring of gas looms beyond the galactic center. When it accumulates some 300 million solar masses worth of matter, it will reach a tipping point. The cloud will begin to funnel into a second ring that orbits close to the center. This inner ring will condense, then erupt with star formation, before spiraling down toward the ravenous black hole. As the cloud falls into it, the black hole will erupt in a blaze of glory visible across much of the universe. Don't wait around for it. Such outbursts happen every 400 million years or so. There is another much smaller cloud that is now on a black hole rendezvous. The cloud, weighing several times the mass of Earth, approached ground zero. This simulation shows the cloud passing within less than a fifth of a light year. It stretched out as the black hole began ripping it apart. Its momentum will carry most of it swirling past the black hole. In time, it will settle into an orbit and slowly but surely collapse into the center. Meanwhile, on a rocky outpost, 25,000 light years from the turmoil of the galactic center, astronomers continue to watch for surprises. They have found ways to track patterns of change shaping our universe over billions of years' time. And yet, it's often the small and sudden events that feed their sense of wonder. Since they started their work, these groups became the first to witness an object making a complete orbit around the center of the galaxy. The star S2 does it every 16 Earth years. Its dimmer cousin, S102, goes around every 11.5 years. No doubt, over the course of their next orbits, we'll answer many of the questions that swirl around their companion, the supermassive black hole. how did it form and shape the galaxy that surrounds it? Will it one day, from the dim heart of the Milky Way, become bright and powerful enough to light up the universe? How did the universe come to be? Why does it look the way it does? How did galaxies form? Planets and solar systems? Life. To find the answers, a series of missions has transported a battery of high-tech instruments above Earth's atmosphere. To peer into the most violent processes in nature and explore the mysterious workings of the high-energy universe. Decades ago, high-energy astronomy was motivated by a number of basic questions. Do supermassive black holes really exist? What are quasi-stellar objects, or quasars? Are they solitary objects in the vast darkness, or are they part of larger structures? In the early 80s, a diffuse X-ray glow was seen filling the night sky. What was it? Bursts of ultra-high-energy gamma radiation appeared almost once a day, lasting seconds, or as long as a day. Are these events nearby, even within our solar system? Or are they extremely distant and highly energetic? Finally, astronomers suspected that supernovae were violent explosions. But what was their exact nature? We now know that they are the final moments in the lives of large stars, and that they are the source of elements that make up our bodies: calcium, iron, carbon, and so on. Because high-energy light does not penetrate our atmosphere, scientists launched a fleet of space observatories designed to capture wavelength bands from gamma ray to infrared. These wavelengths tell us the temperature of matter in an object. Gamma rays and X-rays, tens to hundreds of millions of degrees. Ultraviolet, hundreds of thousands. Visible light, tens of thousands. Infrared, hundreds of degrees. Here is a Hubble Space Telescope image of Cassiopeia A. It shows the visible remnant of a supernova, glowing at about 10 or 20,000 degrees Celsius. Here is an image from the Chandra X-ray Observatory, showing gas heated to tens of millions of degrees. Some of the first images from the Hubble telescope in 1994 captured the galaxy M87. For the first time, astronomers spotted the hot gas swirling around its central region. Knowing the scale of this picture and the speed of the gas, astronomers discovered that within a volume of less than a solar system, there is an object that weighs some 3 billion times the mass of the Sun. Nothing that dense can be anything but a black hole. Over the following years, additional discoveries showed not only that supermassive black holes exist, but they lurk at the core of every large galaxy, including our own Milky Way. This animation shows a black hole moving through space. As an unsuspecting star gets too close, the black hole's gravity tears it apart. That creates a so-called accretion disk of hot gas and dust rotating rapidly around the black hole. Within the disk, charged particles spin off magnetic fields. They channel some of the inflowing matter out in jets so powerful they move at nearly the speed of light. The closer you get to a black hole, the higher the temperatures, 10 million or more degrees. As a result, if you want to study the inner parts of the accretion disk, you have to look at high-energy gamma and X-rays. This inner region can be hot and bright enough to shine across the depths of space, becoming a quasar. The brightest and most active quasars are probably consuming matter at a high rate. In this Hubble image, we see a radio jet coming out of the center of a galaxy. Zooming in, we see the accretion disk and a dark central region. Like Sauron in his dark tower, black holes are known for being terrifying, invisible sources of death and destruction. Black holes are such powerful gravitational monsters that they warp and twist the fabric of space-time. If you get up close, you'd see something like this. An accretion disk visible from both above and below. There is an inner ring caused by light that goes all the way around the black hole before escaping and eventually making it to us. It's actually difficult to get close to a black hole. Gas orbiting the event horizon can never actually reach it unless it first sheds its angular momentum. To understand how this can happen, watch a roller skating maneuver in which one skater catapults the other forward. The skater on the inside whips the partner around, transferring angular momentum outwards and slowing down in the process. Around real black holes, it's magnetic fields that sap the angular momentum of the disk, allowing some gas to fall in while throwing the rest out into space. Like rubber bands, these magnetic fields can stretch until the point where they snap, releasing massive amounts of energy and heating the gas to millions or even billions of degrees. You can see this in the magnetically active corona of our Sun, where superheated gas shines very brightly in X-rays. One of the remarkable effects of a black hole's extreme gravity is predicted by Einstein's theory of relativity. It holds that space-time is not only curved, but twisted. In this computer simulation of particles plunging into a black hole, you can see the effect of this twisting right outside of the event horizon, where particles are being swept around in a counterclockwise swirl at nearly the speed of light. Taken together, the pulling, twisting, and slinging of gas by the black hole leads to ultra-high energy particles and powerful jets. We're just beginning to scratch the surface of what Einstein's theory predicts. Today, the New Star mission is the first telescope to look at the universe in high-energy or blue X-rays. This is a Hubble Space Telescope image of the nearby galaxy Messier 82, seen in black and white. This is what its warm, dusty regions would look like if you could only see it in the red, orange, and yellow of visible wavelengths. Here, the blue reveals hot regions where stars are actively forming. New Star was able to make high-energy X-ray images of the region around the supermassive black hole in the heart of our Milky Way galaxy. It discovered a hot haze created by a swarm of dead stars. When our universe began, it was a soup of hot hydrogen and helium gas. $13.8 billion years later, we are surrounded by a rich mix of chemical elements, ranging from the nitrogen in the atmosphere to the calcium in your bones. This movie follows the evolution of the universe as portrayed by theorists using supercomputers. Filaments of hydrogen and helium form, shaped by the gravity of dark matter. In these filaments, clouds of dust and gas condense and form stars. The massive ones burn hydrogen and helium, creating progressively heavier elements like carbon, nitrogen, oxygen, and eventually iron. When these stars run out of nuclear fuel, they can explode in dramatic supernovae. As the universe grew older, countless generations of supernovae spewed chemical elements into the cosmos, where they condensed into galaxies, stars, and planets. How we know all this is, in practice, a dance between theorists and observers with telescopes including infrared, optical, X-ray, and gamma-ray missions. Huge computational power and theoretical resources have gone into understanding the life cycles of stars. Here is a recent attempt to simulate a stellar explosion in a supercomputer. You can see here that the explosion halts. The authors of the experiment then inserted a theoretical sloshing of gas in the central part of the star, setting the supernova in motion. To find out whether this happens in nature, astronomers enlisted X-ray telescopes to take pictures of the remnants of supernova explosions. Here are images of the debris from the historical supernova remnant Cassiopeia A. The red and the green images were taken by the Chandra X-ray Observatory, which sees the universe in red and yellow and green colors. NuStar has added the blue. This combination gives us a window into the heart of the explosion. These observations suggest that the shape of the explosion was bubbly, consistent with the sloshing mechanism predicted by theorists. Here's Cassiopeia A in all its panchromatic X-ray glory. High-energy telescopes in space are revealing violent events in whole new ways. That includes the most violent of all, a gamma-ray burst with the energy equivalent of 1 to the power of 30 H-bombs. That's 1 with 30 zeros after it. They're the most energetic explosions in the universe. They occur about once per Earth day, and in every part of the sky. In the early days, they were the subject of intense speculation. Aliens in outer space, alien wars. This was an actual newspaper article. In 1998, an Italian and Dutch satellite discovered that gamma-ray bursts actually originate far outside our own galaxy. That means they must be extremely bright, energetic events. A pair of satellites, called Swift and Fermi, were launched to study them in detail and to push the frontiers of high-energy astrophysics. To date, they have detected over 1,000 bursts. Every time the Swift or Fermi satellites detect a gamma-ray burst, scientists get a page that sends them running to their computers to view the data. What they have learned is that gamma-ray bursts are generated by supernovae so powerful their cores collapse to a black hole. A small fraction of the matter flowing into the black hole escapes in jets. When the jet is aimed at us, we see it as a gamma ray burst. Gamma ray bursts are so intense that they can destroy the atmospheres of nearby planets. We appear to be safe, at least for the time being. Imagine a dark and clear night. Overhead, the Milky Way spreads out across the starry sky. The beauty and grandeur of this portion of our own galaxy beckons us to ask our deepest questions. What is the nature of this marvelous universe? How large is it? How did it come to be? And are we alone in this vast cosmos? Astrophysics, the study of the universe and how it works, is central to our quest for answers. We are beginning to find them, thanks to instruments sent up into space, beyond the limiting effects of our atmosphere. High-energy missions, Fermi, Swift, NuSTAR, and Chandra, are uncovering a dynamic universe that is dramatically different from the tranquil tapestry we see with our eyes. They show that the cold, dark reaches of space are punctuated by turbulent forces. Black holes, cosmic explosions, bursts of radiation. That violent energy is very much a part of the universe. As we ask once again the great questions, we know that what we see is just the beginning of a story, written in the great rumblings of the cosmos. A story that is unfolding still.